Okay. Our extended homework is due tonight. The next one, I believe, has been revealed. So there's plenty to work on. I'll have office hours during my normal office hours, but I have meetings with master students at both 12 and 1, and then a meeting with an undergraduate at 2. So I don't know what my availability was. Nothing that says that those meetings will last that full hour. So there may be some time interspersed in there. You're welcome to swing by and see if I have the availability, but I might not. You can see by my lack of passing something out, we don't have an exam quite ready yet, but it should be early next week, according to the TA. I try to turn things around in a week where possible, but I think stress and a very busy workload got to our poor TA. He's feeling it. So let's try to be nice to him and be as understanding as we can. And again, I recognize that that lack of timely feedback does have effects on things like your homework performance and the rest of the class. So it is something that I am keeping in mind as data that I'll carry forward and make associated necessary corrections to grades as needed. Last time we were talking about Chomsky normal form and converting into Chomsky normal form. So when we have a grammar like this, we had kind of 3 steps to do. We needed to first make additional rules converting each, so creating a non-terminal that maps to a particular terminal. So we needed new non-terminals for A, B, and C in this particular grammar. Then we backtracked and replaced all terminals in the original productions with the non-terminals that we had created. That created just strings of non-terminals, which we could then break apart recursively, saying that we have the first non-terminal followed by a new non-terminal representing every remaining non-terminal until there were just 2 remaining non-terminals. And we end up with something like we have there on the lower left. How you name these, I don't really care. You can just use more letters, or you can try to create uppercase letters with subscripts like this for related non-terminals that come from the original A production or B production, etc. Whatever is useful to you is absolutely viable. Questions on CNF before we introduce at least the concept of GNF? We won't do much with this for the moment. We're going to come back to applying CNF very quickly. All right. So all productions of a context-free grammar in GNF is non-terminal arrow, a single terminal followed by 0 or more non-terminals. It's kind of the opposite of a regular grammar where we had a singular non-terminal followed by 1 or more terminals. 0 or 1 non-terminal, I guess. But in this case, we just have a single terminal followed by more non-terminals. And this is very much like transitions in a state machine. That is the way to think of how GNF makes sense. That one terminal is going to represent a transition, and the rest of the non-terminals are going to be the remainder of the strings objects that we need to resolve via some sequence of productions that move terminal at a time. So this is very useful for translating between grammar and state machine, which is what we will see when we come back to it. Go ahead and spend a minute or so, write a grammar of 4 or more productions that adhere to GNF. It's for practice, so you have something to look back to. Anyone have any questions about if their form adheres to GNF or not? We can come back to this as needed, but I am going to move forward just because I know what's coming and I would rather have more class period to get further into it than less class period. So we're going to go back into the membership question, which we attempted to answer with brute force parsing, but the question behind it, is this query string in the language defined by this grammar? That is the membership question. And that maps to what a compiler does with a program. Is this program in the language defined by this grammar? Are there syntax errors in this program? Very similar types of questions. So it turns out that this is a much easier question to answer if the grammar is in CNF. So we are going to go through a process, the cubic process that was hinted at earlier, and define and start to understand the CYK algorithm. This will become your first programming project. So it is very worth understanding this to the best of your ability. So input to CYK is going to be a grammar in Chomsky normal form. So productions in those two types, non-terminal arrow, single terminal, non-terminal arrow, non-terminal, non-terminal. We're going to break down the string that is the query string into its associated characters. So C sub 1 up to C sub L are individual characters in the query string. You can think of this as tokens in a program or characters in a string. So L is the length of the string. There are L characters in a string of length L. But then we also need to define substrings for this procedure. So we're going to call W sub ij as the substring between positions I and j, and it's going to be inclusive. So it's unlike this substring method in Java, where the first parameter is the character's first position, and the second character is the next character after that. Instead, we have something that is inclusive. So W sub 1, 3 would be characters 1, 2, and 3. But that would be starting at 1 indexed and not 0 indexed. So shift your brain from a 0 indexed brain to a 1 indexed brain for this. So now we need to define a capital N sub ij. This was a little bit confusing. It's the subset of non-terminals in the grammar that can produce the substring wij via some sequence of productions. Basically, if we started at a non-terminal in N sub ij via some sequence of productions, we could produce the substring wij as output. So we can say, by the time we reach this point, that the entirety of W is in the language of the grammar if and only the non-terminal S is in this N sub 1N or 1L, whatever we want to use for the number of characters in the string. So we care about answering that question. It turns out that we have to take a dynamic programming approach to get there. We're going to solve all of the subproblems to this and use the solutions to those subproblems to build up a solution to this. So break out your algorithms memory and dig up dynamic programming from it. Does anyone want to take a stab at telling the class, what is dynamic programming? How did you come to understand it? And what is it? Yeah.
Keeping track of important or computationally complex values.
Yeah. Yeah. So I would even shorten that to something like caching. is a great way of understanding. We're going to, the larger problem is so complex to figure out that if you were to brute force, ask yourself how to do that, it would take an exponential amount of time. The example that I like to break down for this is the Fibonacci sequence, because we've all seen it before in some class or another. Who remembers the Fibonacci sequence? Who doesn't remember the Fibonacci sequence? So the nth term of the Fibonacci sequence is defined by the n minus first and the n minus second term. So you're going to add the two numbers that come before it. The first two numbers are stated to be 0 and 1. So that is the 0th Fibonacci number is 0. The first Fibonacci number is 1. Then 0 plus 1 is 1. That becomes the second. 1 plus 1 is 2. That becomes the third. 1 plus 2 is 3. That becomes the fourth, etc. forever. Now, there's one way to think of solving something like Fibonacci of 7. So I'm going to just represent Fibonacci of 7 as the number 7. And if we were asked, what is Fibonacci of 7? Well, you could break this down into, well, to answer this question, I need to answer Fibonacci of 6 and Fibonacci of 5. We don't know either of these offhand, so we'll break this down. And you can see just how much repeated work we end up doing. We're going to ask Fibonacci of 7 once, 6 once, 5 twice, 4, 1, 2, 3 times, 3, 1, 2, 3, 4 times. So far, it's going to end up being another time when we break that apart. So it ends up being way more work than it is if we could calculate Fibonacci of 0 and 1, use that to calculate Fibonacci of 2, use that to calculate, but recognize when you're doing that, you're caching the results of smaller values of the Fibonacci sequence. So as you cache that, you take an exponential problem and you turn it into a linear time problem where we take this result to answer that, but it's a lookup for every other time we would need it in this process. And you come up with a bottom-up procedure that is much more streamlined than this top-down procedure. And you just need the extra memory for looking up the computations of the subproblems. So whenever you have that, you have a dynamic programming problem. And what you need to store is something that is relevant to the solution to a more complicated version of that problem. It will end up breaking down into smaller subcomponents that you have already solved. And then you don't need to solve the same subproblem over and over and over again. They become lookups. So usually you have some kind of table that becomes your lookup table. So the lookup table for the CYK algorithm is going to be another half table, just like with DFA minimization. So it's worth noting that answering the subquestion n sub ii, that means a substring of length 1, it's very easy. We just look in the CNF grammar whether there is a production that is non-terminal, arrow, that terminal. And that terminal is the terminal in the ith position in the string. So very easy lookups. For every more complicated question, then we can say a non-terminal generates that substring if and only if there is a middle point in this that we're going to call k, such that we break the substring down into a first half and a second half. They don't have to be the same size, but a first portion and a second portion. And in our table, we've solved the first portion and the second portion. We can see whether there is a non-terminal arrow, a arrow, something in the lookup on the left portion and something on the arrow of the right lookup. Again, this will make way more sense when we do this as an example, but the non-terminal production ends up being from the left side and the right side of this middle point of the string. So we need to look through every possible middle point and get an understanding of how can we break this apart such that the grammar can construct this substring. We store the sets of productions, the sets of non-term left-hand sides that can generate that, and that becomes the solution to the subproblem as we build up more and more complicated, longer versions of W sub ij with a wider range between I and j. Eventually, we have between 1 and n, and we check if S, the initial production, can produce the entirety of the string based on the work that we've done. All right. So series of steps, compute all possible n of size 1. So you're going to look at substrings of size 1, kind of a window passed over the string of all substrings of size 1. So look at the first character, then the second character, then the third character, up to the last character. And that's what each of these n's stand for. Substring starting at 1, ending at 1 is the first character. 2, substring starting at the second character, ending at the second character, etc. So all substrings of length 1. Then you're going to compute all where the difference is 1, the difference between I and j. So you're going to calculate the substring 1, 2, 2, 3, up to L minus 1, L. And then you're going to do that for all of difference 2. So you'll calculate 1, 3, 2, 4, up to L minus 2, L. And you continue this process until you generate n sub 1n, where n is the length of the string. So it really is just filling in a half table, row at a time. Let's go through this process and see if we can finish it off within the bounds of class. So here is our grammar in CNF. And I'm just going to start building the table because I don't need any further slide assistance for this. See, we're going to end up with AABBB. So this bottom needs to be 1, 2, 3, 4, 5. Next row will have 1 fewer. Next row will have 1 fewer. Next row will have 1 fewer. Did not happen. And the next one will have 1 fewer. That also did not happen. So what this half table will represent down here, we have n sub 1, 1. Here we have n sub 2, 2, n sub 3, 3, n sub 4, 4, and n sub 5, 5, where 5 is the length of the string. This is that window over the string, looking at character by character, first character, second character, third, fourth, fifth. Then here we have n sub 1, 2. Here we would have 2, 3, 3, 4, and 4, 5. Here we would have n 1, 3, 2, 4, 3, 5, n sub 1, 4, and 2, 5, and n sub 1, 5 in the very last spot. Any questions on how I came up with those indices? Trying to minimize writing in the box because we're going to need to write other things in the box. This represents every possible substring of this string. So the first step is going to be to fill out this first row. So we're going to be looking for any productions that lead to terminals. And we're going to be filling in information here based on the set of the non-terminals that can produce those terminals for that window on the string, or that substring. So the first one is A. This represents 1, 1, substring that starts at 1, ends at 1. So what non-terminals can produce lowercase a? And it is just A, the capital A. So this is, everything in here is a set, but it's the set that contains the non-terminal A. And that is going to be what we put in this box. Questions so far on how we got that? N sub 2, 2. Same thing. Which character, which non-terminal produces that terminal A? That is just the non-terminal A. 3, 3 produces B, and it comes from B, and only B. Same thing for 4, 4, and 5, 5. The first row is the easy row. It'll get more and more complicated each row we move up. Any questions? This is very important to know, so please ask questions now before we get into the next more complicated row to make sure that we're all on the same page. Are we okay? No questions? All right. Now we're going to be looking at substrings of length 2. So I'm going to erase these, and now we're going to be looking at, we're going to start looking at the productions of form non-terminal, arrow, non-terminal, non-terminal. So I'm going to bring this AA down for a second, and we're going to split this apart into a left-hand side and a right-hand side. There's only one place to break this in the middle. We need to now identify substrings that are a left half and a right half. So where does this A come from? This A is n sub 1, 1. So if we look at n sub 1, 1, this is A. This is n sub 2, 2. To get this A, that came from here, the second character in the string. So n sub 2, 2 is also an A. So now what we want to do is we want to take the cross product of the left-hand side and the right-hand side, giving us all such tuples of an element from the left-hand side and an element of the right-hand side. There's only one such tuple for this. It's the tuple AA. And that tells us that what we're going to go look for in the right-hand side of a production here is AA. Is there any right-hand side of a production with AA? There is not. That says that it is impossible to produce the substring AA from any one of these non-terminals via any sequence of productions. And what we put in this box, n sub 1, 2, is the empty set. There were no productions that generated one such tuple from the cross product of the left-hand side and the right-hand side. Okay, that was one box. Now we're going to look at the next substring. This produces AB. Left-hand side is n sub 2, 2. Right-hand side is n sub 3, 3. This produces A. This produces B. We take that cross product, we end up with a tuple AB. Anything AB on the right-hand side of a production in our grammar? What are they? S and B. That's what we're going to put in this box. Every possibility that can generate that. So even though there's only one tuple, there were two right-hand sides in the grammar that could produce that tuple. So we put two elements in this set. Any questions on that? Yeah.
Does the order matter?
Yes.
It's like S goes to BA.
Yeah, if it were BA, we would not allow it. The order does matter in our cross product.
Okay.
So only if there were a BA somewhere in the options here would we accept something that was a BA over there. So yes, order does matter. Any other questions? We perfectly understand how this was derived. We can move to the next one. Get that B. This is n. I'm going to stop writing now the n sub and kind of just refer to it and point to it. because now we know where that comes from. If you'd like to continue writing it, you're more than welcome to. It's just going to get very tedious, and I'll leave my marker dry. So this B came from n sub 3,3, which was a B. This is n sub 4,4, which is also a B. The cross product of a B and a B produces a tuple of BB. Is that a right-hand side somewhere in our grammar? Yes, it is. It comes from A. So A is what we are going to put right here. Again, this BB shows up right there. The left-hand side that can derive that non-terminal, that sequence of non-terminals, is the A. The left-hand side is what we put in the box. Last one, 4, 5. Turns out that we also have a B and we also have a B. When we refer to those down here, it's still a B and still a B. So we get exactly this same setup. Instead of the left-hand side and right-hand side being BB, we get BB. So the answer is going to be exactly the same. We're looking for a BB on the right-hand side of a production. The left-hand side of that is an A. All right, moving up a row, increasing the difficulty. We're now going to pass over a window of size 3. So we're going to start from the left again. N sub 1, 3 is the first 3 characters of the string. We're going to look at AAB. And now, there are 2 possible middle points. We could break it here, or we could break it here. Each of these are going to have their own branch. For this one, what is the left-hand side in terms of the indices? This is n sub 1, 1. Just the first character. What is the right-hand side?
2, 3.
N sub 2, 3. We've solved both of those. So the left-hand side comes from here. That's an A. And the right-hand side, 2, 3, was S and B. So when we take the cross product of, these should have sets around them, A and SB, we end up with 2 possibilities, AS and AB. Let's look at the right-hand side. What is AA? N sub 1, 2, which is empty. The cross product of empty and anything will never generate anything of interest. So I'm just going to bring that down, and we're not going to do any further work here because it's unnecessary. Do we see why that is? Cross product is going to be some combination of something from the left-hand side and something from the right-hand side. If there's nothing in the left-hand side, you can't come up with a tuple of elements because the left-hand side will always be empty. Therefore, there will be an empty 0 possible strings here. So what we're going to do is union together all possible right-hand sides that could produce either of these. So what are all non-terminals that can produce either AS or AB? S and B. That's what goes here. For the next one, we're going to be looking at ABB. We can break this here, we can break this here. What is this A? 2, 2? Yeah, this is N sub 2, 2. What's the BB? 3, 4. Again, we've solved everything in both the first row and the second row. When we split a substring of size 3 into 2 pieces, one will be of size 1, one will be of size 2. So we know we're going to have them solved, which is nice. What's the AB?
The AB.
From here, which sequence do we have here?
2, 3.
Yeah, we have n sub 2, 3. And here we have, 4, 4.
Oh.
You can almost see it from here. We end up with 2, 3, and then 4, 4. To get the same, we want to consider between 2 and 4. So we can either have 1 here and 2 here, or 2 here and 1 here, and they're always going to be distinct. The last index here is going to be before the first index here. So n sub 2 is the set containing A, n sub 3, 4 is the set containing A. Anything AA on the right-hand side of our grammar? No, this will add nothing to that box. Let's look at 2, 3, and 4, 4. 2, 3 is S and B. 4, 4 is B. So this is either SB or BB as our options. Anything SB or BB over there?
A.
A. So here we have empty, union everything from SB, union everything from BB, which is just nothing, union nothing, union the set containing A. Might be the way to think about this in a way that helps you with your set notation. I'm kind of skipping around a little bit and shorthanding a little bit, but A is all that goes there. All right, for 3, 5. This is the substring BBB. So we're going to have 2 copies of BBB. Split 1 here, split 1 here. What do we have? What are our components on the left-hand side? We're starting at 3, so we have 3, 3, and 4, 5. And here we have 3, 4, and 5, 5. All right, 3, 3 is B. 4, 5 is A. 3, 4 is A. And 5, 5 is B. Anything BA over there? No. Anything AB over there? Yes. Both S and B. So that goes in this box. All right, moving up a row, moving up in difficulty. Any questions? Do we see how this is dynamic programming? Every time we refer to one of these, it's a prior solved problem. So it's just a lookup. All right, back to strings of size 4, AABB. But now we need how many copies of the string? Someone shout that out. How many copies? 3. All possible midpoints. We can break it after the first character, break it after the second character, or break it after the third character. They are creating a union of 3 different left-hand sides and right-hand sides. What is this A? 1, 1. What is this right-hand side? 2, 4. Luckily, we just finished solving that row, so now we can use its solutions as lookups. Yay! How about this one? What's the left-hand side? What's the right-hand side? 1, 2, and how about this left-hand side and right-hand side? We have 1, 3, and 4, 4. All right, let's fill in based on our table. 1, 1's lookup is an A. 2, 4's lookup is also an A. 1, 2's lookup is empty. I'm going to stop thinking about it. 1, 3's lookup is S and B. 4, 4's lookup is B. This produces SB and BB. So our options are AA, SB, and BB. What left-hand sides produce any of those? Just A producing this BB. There's no SB and there's no AA anywhere. So this BB can be produced by A, and that's what goes in this cell. Yay, erasing and drawing more things. Now we're looking at a BBB. We need 3 copies. The row that we're on, the 4th row minus 1 is going to be the number of copies that we're going to write. So we have A, B, 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 A, B, 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 A, B, B, B. Break out the first character, second character, and third character. Again, left-hand side and right-hand side. Here we have 2, 2. Here we have 3, 5. Here we have 2, 3. Here we have 4, 5. Here we have 2, 4. And here we have 5, 5. 2, 2, look up in the table, that's an A. 3, 5, look up in the table, that's S and B. That gives us the options AS and AB. 2, 3, look up in the table is S and B. 4, 5's look up in the table is A. That gives us SA and BA. 2, 4's look up in the table is an A. 5, 5's look up in the table is a B. This gives us AB. All right, combinations. What are the left-hand sides that we can get from AS, AB, SA, BA, or another copy of AB? I heard it somewhere out there. Confidence. S and B. That comes from the AB and the AB, nothing AS, nothing SA, nothing BA, but AB can be produced by S or B. So that's what we put on the table. Yay, we're done with the 4th row. One last thing to do, and it turns out that we really only care about one thing in this entire table, and that is S present here? So we can terminate as soon as we find S, or we have to go through the entire thing to prove that S is not there. And that tells us whether or not this grammar can produce this string. But now we have all of the information in our table to be able to finally answer that question for sure. So let's do it. We're going to go over the entire string. How many times should I write this string? 4 times. So we're going to have A, B, A, B, 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 A, B, 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 A, B, 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 and A, B, B, B. Great. We'll split after first character, second character, third character, and 4th character, creating our wonderful set of indices 1, 1, 2, 5, 1, 2, 3, 5, 1, 3, 4, 5, and 1, 4, and 5, 5. Every possibility of the associated breakdown. 1, 1 was an A. 2, 5 was S and B. This produces AS and AB. We found the right-hand side with an S in it. We can save my poor arm and not have to do any of the rest of this work. So since this can be produced by an S, we know that S is in this set. And in fact, B would also be in this set if we continued this work. But we just care about the S. That tells us that there is a way via this grammar to produce this string. Let's see if we can find that path. If we started with S, we could produce AB. From AB, how do we break it down to start to get this string? Any guesses? This A becomes something? Probably a BB, or do we want to set that to be an A? Yeah,
The A becomes an A and the B becomes an AB,
okay.
and then the B becomes another, yeah, so then.
Yeah, what does this A become?
Lowercase A becomes another lowercase a, and then the B becomes AB again. And then,
So this becomes another lowercase a. We have A capital B. What are we doing with this capital B?
another AB.
Okay.
And the A becomes the BB and the.
Yeah. So this A becomes a BB. And this B becomes a B.
And then those.
Both of these become Bs?
Yeah.
Yeah. We end up, I'm skipping a step here, but A, B, 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 B. So that's the logic that we're used to in terms of using our productions to produce the string. But now we have an algorithmic way of proving it for an arbitrary grammar and a grammar that is larger. It was still a little bit of a challenge to see the path to produce the string in a grammar that is this small. When you get a grammar the size of the grammar for the Java programming language, or really any programming language, good luck. The branching factor is so large that it's not going to be something that's possible to manually do. So we're going to want a computer. And this is the most generic way that for any context-free grammar, we can ensure that this process can answer yes or no, that we can derive that string from that grammar. So we first have to convert that grammar into CNF. Once we have a grammar in CNF, this process always works. That said, it's a little slow. I said it was cubic. Why is this a cubic runtime? When we say cubic, we mean it really has 3 dimensions. What are those 3 dimensions? You can think of those dimensions as loops inside of loops, if you would like. If you're writing this as a program, what are your loops?
Well, just naturally for every string, you're going through every possible substring. So that's already
Yeah.
squared.
Yeah, so we're going to say for each row,
Yeah.
Inside of that, we have for each column. And inside of that, we have for each midpoint. And there are n of these based on a size of the string being n. There are n of these. We end up only doing half that work in total, but that's okay. And each midpoint, there were the current number of row. We have, if this is going to be R, we have R minus 1 possible midpoints. So this will scale as that scales and create another dimension that is in fact based on n. So this ends up being cubic in nature. We're turning this into a program. This becomes a great place to start just in terms of how do I structure this? Well, it's going to be a triply nested loop. Any questions on this procedure? Do we feel like we could go implement this? Yeah,
I just have a question. When you're doing when you get to the end, you can show that W is part of the language, right?
yeah,
But can you verify that using the table and tracing steps back somehow?
yes.
If you had like 100 characters long, you couldn't just like figure out the productions. Show
Yeah,
that.
you would need to be able to show this breaks down into the 1, 1, and 2, 5. So that tells us the S is going to come from the AB portion of this. And then when we break that down, that 1, 1 stays, which means that it should go to a terminal. Then the 2, 5, we need to break down where did that 2, 5 come from. So we need to look back at if we stored in addition to just the S and B, if we stored where in these breakdowns that SB came from, that would tell you where the left-hand side and the right-hand side are. So this actually does, and you can store and trace the path embedded in this table, but you do have to store when you add any particular character, what breakdown that came from. Great point. All right, I will be revealing this assignment. I am anticipating giving people about 3 weeks for it. So it's not something that's complicated enough to require 3 weeks, but that said, you're going to be working on some homeworks as well throughout this period. As there is a lull in the difficulty of the homeworks, I highly recommend working on this on the side. For instance, the next homework that you are going to receive is not quite as difficult as the current one. So I would recommend getting started on this next week. Get started, get stuck, even if it's in the design phase of this. And I will also make sure you look at the assignment. There is a link in the assignment to a visualizer for this. You can put in a grammar in CNF and watch it get solved. And that can help you to debug your program to make sure that it's going through and doing the correct work. I also have some input and output files for you to practice with and make sure that your program does what it's supposed to for those test cases. You can throw those into the visualizer. All right, I have office hours, my only for sure office hours starting now. So if you'd like some assistance, this is the time to get it. I will see some of you soon.